Hello. Today I would like to present our work on tracking the motion of athletes using one or more cameras. Since we now have powerful deep learning architectures that can reliably track people walking around, this may sound easy, but it isn't. Existing training data sets are captured indoors or are simulated and don't generalize well to unusual activities, like slaloming. Here, the center of gravity of the person is not necessarily above their feet, and as you could see, a state-of-the-art method trained on the 36 million images of human H36M dataset did poorly. One solution would be to use more training data, but where to find it? Existing datasets are not designed for this. In the specific case of skiing, we are fortunate to have a collaboration with a group from ETH Zurich that generated and annotated 800 timeframes acquired using multiple cameras with overlapping fields of view. This has allowed us to properly train a network and get the result we just saw. However, in practice, a hardworking PhD student had to spend a lot of time annotating, and this will not scale. We have therefore been looking into weakly supervised approaches that make it possible to obtain these kinds of results with very few annotations. Because we have been working for a long time with multi-view stereo, we started by looking into using multiple calibrated and synchronized cameras. We use the annotated views in the usual way and the unannotated ones to write a multi-view continuity loss. The poses predicted from the two images acquired at the same time should be the same up to a rigid transformation. Unfortunately, this turned out not to be as straightforward as we had hoped, because poses can be consistent and wrong at the same time. We therefore had to add a number of additional losses to penalize such consistently wrong solutions. With these additions, we eventually obtained much more convincing results, such as the one shown here, but at the cost of a far more complex approach to training the network. To move beyond that, we started investigating a different tack. Could we devise a geometry-aware representation that would make the training easier? Going back to traditional approaches to 3D pose estimation, why do networks require large databases for effective training? There are at least two reasons. First, we are trying to estimate many degrees of freedom. Second, going directly from an image to a 3D pose requires a very deep net. Hence, it makes sense that training such a net would require much training data, but raises an interesting question. Can we learn a representation that has fewer degrees of freedom for specific activities? The answer is yes, and we got our inspiration from the novel view synthesis work depicted in this animation. One can learn a scene representation that makes it possible to take as input an image and rotation vector and to resynthesize a rotated image. So, how can you do that? One way to start from a regular autoencoder that is trained to resynthesize an input image. It can be modified as follows. The latent vector that is the output of the encoder becomes an L/3 matrix that can be rotated by being multiplied by a 3/3 rotation matrix, Rij. This yields a new latent matrix that, when decoded, ought to produce an image a camera rotated by Rij ought to produce. Such an encoder can be extended for our purposes as follows. We divide the latent representation into two parts. One is represented by an L/3 matrix that ought to capture the pose of the subject. The other is a regular vector that ought to capture the appearance. At training time, We use pairs of images acquired at the same time, but from different viewpoints, and swap the appearance and vectors before decoding. This ensures that the appearance vector is independent from viewpoint and that the pose vector captures the geometry of the person. In short, the pose of a test subject can be represented as an L/3 matrix that can be represented as a point cloud. By decoding this point cloud using the appearance of someone else, we can synthesize the image of the first person with the appearance of the second. In short, given a set of multi-view images, we can train in a completely unsupervised fashion a decoder that produces low-dimensional representations of the poses. We then only need a shallow network to convert this representation into 3D pose, and this shallow network requires far less annotated data than a traditional deep one. We tested this on human 36M. You can see here the performance of a ResNet compared to ours as a function of the number of annotations. In the very low annotation rate regime, we do much better. However, in the higher rate of annotation regime, the first method I presented tends to do better. This may have to do with the fact that we did not use enough different people to learn the initial representation and should be looked into. Another problem with the technique I just presented is that it is not always possible to have multiple synchronized cameras. We are therefore investigating what can be done with video sequences instead. To reformulate our approach across time instead of across views, we first separate our latent representation into a time variant and a time invariant one, which play the same role as the earlier geometry and appearance latent vectors. When learning the time variant part, we use contrastive learning to exploit the fact that it is usually more similar at small time intervals than at larger ones. We incorporate a bounding box detection network so that the network can be deployed at real sport events. And we enforce physics-based constraints to speed up convergence during training. This turns out to work very effectively to train a single camera system to compute the pose of divers and of skiers using very little annotation data. As an aside, this is not the first time we embed physics-based constraints into deep network architectures. This is a ball tracking algorithm we developed some time ago, encoding into the system the fact that the ball motion is parabolic until touched was key to good performance. This is because ball tracking is a surprisingly difficult task for several reasons. First, the ball moves fast and motion blur makes it hard to see. It's actually here. Second, its appearance may be very similar to that of other objects or people, making it even harder to see. Third, it can be occluded during extended periods of time. As a result, ball tracking algorithms that rely only on physics and ignore the ball's interaction with the people do not do well. By contrast, we explicitly model the concept of ball possession, and we only use physics-based constraints when the ball is not in possession. As a result, we get much more realistic trajectories, such as the green one shown on this slide. So, the core message of this talk is that deep networks are hard to train in sports scenarios because we rarely have large enough databases. However, we can exploit multi-view geometry and physics-based constraints to develop effective approaches to supervision, which largely mitigate this problem. Which brings me to my conclusion. Pose estimation in sport has a long history. When deep networks captured the field by storm in 2012, it was said that everything else was going to be swept away. That's not exactly what happened. You still need to understand physics and geometry, while the deep nets give us the foils we need to go much faster than we used to. So in short, geometry and physics still rock. Thank you very much. And of course, I also have to thank all the people whose work I presented today and whose name appear on that slide.